Hello everyone, I'm Maulik Bhatt, a PhD student at University of Illinois Urbana-Champaign. Today I'll be presenting our work on efficient constraint multi-agent trajectory optimization using dynamic potential games. As autonomy is rapidly growing, autonomous agents will have to interact with other agents in the environment. For example, autonomous cars and delivery drones will have to reason about the impact of their actions on other agents and navigate accordingly such that they don't cause collisions and reach their goal location safely. In all such interactive settings, dynamic game theory provides a strong mathematical formulation to deal with such scenarios. Several recent works have shown that seeking Nash equilibria of the underlying games in such interactive settings results in highly effective trajectories. Consider a scenario of three agents in the environment where two drones are carrying an object to its goal location, and there are two other agents moving to their goal locations individually. Each of them have their own objectives and which are denoted by J's, and they have their own dynamics. Furthermore, each agent has to satisfy some safety constraints such as reaching their goal location, avoiding collisions with others, and equality constraints for drone to carry objects safely. Outcome of such interactive settings are generally modeled through generalized Nash equilibria, where essentially no agent has any motivation to unilaterally deviate from the Nash equilibrium strategies while satisfying constraints. It should be noted that here G denotes the safety constraint between the agents such as collision avoidance, and it essentially captures the interaction among the agents. However, solving for generalized Nash equilibria is a really difficult task because it requires solving coupled constraint optimal control problems, and it is really difficult to solve it in real time and computationally intractable for most real-world scenarios. Our key idea is that under certain cost structures, constraint trajectory planning problem can be cast as a constraint potential dynamic game. And the generalized Nash equilibria of such games can be solved by computing a single constraint optimal control problem solution. With this idea, we can convert the problem of solving n coupled optimal control problems into a single optimal control problem for the case of constraint potential dynamic games, because we can have an existence of a potential function P, which can be optimized very efficiently and in real time by using any generic optimizer. Now we provide sufficient condition for existence of constraint potential games. Consider the previous scenario where each agent's objectives are sum of their running and terminal costs. If each agent's running and terminal costs depends only on their own states and actions, then there exist these two functions Q and R such that the trajectory planning problem will become an instance of constraint potential dynamic game with a potential function as shown here. Now that we have a single potential function with constraints, we can solve it using any generic optimizer. And in particular, we use Ultro to solve in our case. In order to showcase the capabilities of our method, we consider this 4-agent planar navigation scenario, where each agent are tasked to move towards their goal location with the constraint of avoiding collision with other agents. As we can see, we are able to generate highly interactive and effective trajectories. Furthermore, because of this reduction into solving a single constraint optimal control problem using this game theoretic idea, we found out that our solver is about 20 times faster than the state of the art. Furthermore, we implemented our algorithm in a receding horizon fashion in a real-life scenario where two agents carry a rod towards their goal location while navigating in close proximity to humans. As you can see, as the robots gets close to the human, the drones change their orientation and navigate safely around humans and afterwards reach its goal location. This showcases the real-time capabilities of our method as well. In conclusion, we propose a solution to the problem of fast and efficient multi-agent interactive trajectory planning. Our key idea was that game theoretic interaction will become an instance of constraint potential game that can be solved tractably and efficiently in real time. And in future, we would want to investigate whether potential games can be used for efficiently generating feedback generalized Nash strategies. Thank you.